This section, we're going to solve differential equations with power series. That is, the answer is going to be a power series. Now, power series is nothing more than an infinitely long polynomial. For example, you can have a number, call it a sub 0, constant, plus a constant times x, plus another constant times x squared, plus another constant times x cubed, forever and ever and ever. If it ends, it's called a polynomial. If it doesn't end, we call it a power series. Now, if you wanted to write this down in sigma notation, a couple of comments. You need to realize that a sub 0 is the same as a sub 0 times 1, and that's how I'm going to write 1. And then the power of x is just 1. Now, if you want to write this down, what you need to do as a sigma notation, now the reason I choose sigma notation is because sigma means sum. We are adding. And you want to look to see what looks the same in each term. Well, they all have an a and they all have an x. Okay? Then I notice what's changing. That subscript is 0 and then 1 and then 2 and then 3 forever. So I'll call that subscript n, and I'll say n starts with 0 and it goes forever. 0, 1, 2, 3. Then I notice, oh look, the power of x is exactly the same as those subscripts. And I call the subscript n, so I'll call the power of x n. I just wrote this infinitely long series using sigma notation. Now, that was the easy part. Now we have to learn how to add two infinite series. Suppose you have the summation as n goes from 3 to infinity of c sub n x to the n minus 2 plus the summation as n goes from 1 to infinity of c sub n x to the n plus 2. Now, just so we're on the same level, let's talk about what this here means. Well, it's sigma, so we're going to be adding. We're going to be adding that to itself many, many times. But that's going to change. It's going to change as n changes. First, n starts with that number. So this piece becomes c sub 3 x to the 1, because 3, n is 3, 3 take away 2 is 1, plus. So first n is 3, and then 4, and then 5, etc., etc. So we dealt with 3. Now we'll let n be 4. So that's going to be 4. It's going to be c sub 4 x to the 2. Because if n is 4, and you take away 2, just like it says to do in the power, you get 2. And now n is 5. So it's going to be c sub 5 x to the 3. Because 5 minus 2 is 3. And then n is 6. So it'll be c sub 6 x to the 6 minus 2 or 4. Forever and ever. That's what that's going to be. And that was this piece, of course. The next piece will be similar. Now, the instructions is to write this, just using not x to the n minus 2, not x to the n plus 2, but say x to the k. When both of these, and when this infinite series in this infinite series, also called the power series, to start with, to have x to the k. So we're going to have a summation. We're going to have c to something that we didn't determine, and then we're going to have x to the k. Now, we just need to be careful. First, n is 3. That means first, that power will be 1. 3 minus 2 is 1. What did I get 3 from again? N starts with 3. So first that power is going to be 1. Then when n is 4, so that's the next number after 3, 4 minus 2 will be 2. And then n will be 5. And 5 minus 2 will be 3. The power of x is just going 1, 2, 3. Well, if I let x start with 1, and it goes all the way up to infinity, then first that power will be 1, and then 2, and then 3, just like we want. Now, what's the subscript? The first subscript is going to be 3, because that's the first number n will be. And then when n is 4, that subscript will be 4. And then when n is 5, the subscript will be 5. I want the subscript to start with 3. Well, k starts at 1. Oh, add 2 to it. It'll start with 3. So I rewrote this first term right here. And it does have x to the k. Now, we're going to do the same thing with the next term. Now, with this other term, we also want to have an x to the k. Now, when n is 1, so we want to know where k starts with. When n is 1, then that power will be 3. So we want the power to start at 3. I don't care what n equals. I don't care what k equals. It has to start with 3. Initially, I care what n is. N is 1. 1 plus 2 is 3. The power starts with 3. To get about n, I want that power, whether I call it k, or k plus 7, or Harvey. I want it to start with 3. Well, what should k be so that power is 3? The answer is 3. If this power happened to be k plus 1, and I want it to be 3, I would have put 2 there. I let k start with 2. If it said k minus 1, and I want the power up here to start at 3, I would have let k start with 4. But everything's fine now because I don't want it to be anything other than k. If I want this power to be 3, I start at 3 and I go all the way up to infinity. Okay, now we need to deal with that subscript. We need to deal with that subscript. We need a little space. I'm just going to move over to x to the k. Move it to the right a little bit. When n starts at 1, that subscript will be 1. When n is the first number it's allowed to be, that subscript will be 1. So I want this subscript right here to be 1 when k is its first number. But k is 3. So all you have to do is put down k, well that's 3, and say, oh, when I take away 2, I get 1. And we are done. Well, so let's continue. We're not done. We're done with these 2 major steps. Now, I could write this down as one summation. It's the summation of this plus the summation of that. Now, before we can have one summation, we need to realize that this is starting at 1 And this one's starting at 3. 1 and 3, which is the largest number of those two? 3. So when k is 1 and 2, I have to break that one up. That is, when k is 1, what's in here is c is 3, plus 1 plus 2 is 3, x to the first power. I won't write 1. Plus, now k is 2. K is first 1, then it's 2. Well, 2 plus 2 is 4, x to the 2. This is where k is 1. This piece was where k is 2. Not plus 2, excuse me, but where k equals 2. And remember, k goes from 1 up to infinity. K is 1 and then 2, and then it's 3, 4, 5, 6 to infinity. Well, I can write the 3, 4, 5, 6 to infinity as a summation as k goes from 3 to infinity plus c sub k plus 2 x to the k. What I've written so far is just this. So I have to add on the rest. The summation as k goes from 3 to infinity plus c sub k minus 2 x to the k. Now we have two portions, or two concrete pieces. We have this piece plus that piece. Well, that piece we can factor out an x to a k. But before so, we have to realize that the summations are the same. They're both having k going from 3 to the same number, whether that number is infinity or 17. K is going from 3 to the same number here as it is here. Of course, infinity is not a number, but we'll let that comment go. So we have the two isolated terms in front plus. Now, when we combine this term with this term, by design, we know we can factor out x to the k. The summation as k goes from 3 to infinity. Remember, we made both of these x to the k. That was the instructions. So we have the summation of ck plus 2 times x to the k, which I factored out, plus the summation of c sub k minus 2 times x to the k. This only works if they both are starting at 3 or 7. They're both starting at the same number, and they're both going to the same number. So that here is the answer. You may have to look at this 3, 4, 200 times. Whatever. Just look at it enough times so you get it. You have to be able to do this. Now let's try another one. Suppose you have the summation as n goes from 2 to infinity of n times, we'll call it n minus 1. N times n minus 1 times c sub n plus 1 times x raised to the n plus 2. And we want to add or subtract the summation as n goes from 1 to infinity of n plus 2 times c sub n x to the n minus 1. We want to add these. What that means is we want these both to be x to the k. I'm going to do it one by one. Let's work on this one first. It's going to be the summation as k goes from some number to infinity. And let's see, and I want to have x to the k. First I'm going to work on this, and then I'll get this, this, and that. When n is 2, the first number that n can be is 2. This power will be 4. Well, if I want this power to start at 4, I should just let x start at 4. I meant to say k start at 4. Now, when n starts at 2, that will be 2. Okay, so this is n, and when n is 2, that will be 2. So I want it to be 2, but k is 4. If I take away 2, it'll be 2. Now, don't think, oh, you want it to be 2? It's 2. Fair enough, it's 2. But then when n is 3, that's still 2. When n is 3, then that should be 3. Well, k, which starts at 4, take away 2, that's 2. Now, there's two ways of getting the next one. You can say when n is 2, that's going to be 1. So if you're at 4, and you take away 3, that'll be 1. Or you can be slick and say, you know what, whatever that is, that's 1 less. And if you have a number, and then you take away 1 from that number, you 1 less. So I have a little mistake here. I'm pretty sure I said it right. Just had 4 in my mind. If k is 4, and you take away 2, then you'll have 2. Well, I have this number, and I take away 1 more. You take away 2 from k, and then you take away 1 more, you took away 3 from k. Okay, now the subscript of c. When n is 2, 2 plus 1 is 3. Well, k starts at 4. If I take away 1, it'll be 3. And there it is. Now we play the same game for this one. The summation as k starts at some number and goes all the way to infinity. And we want it to be times x to the k. Well, when n is 1, that power will be 0. Well, what should k be so it's 0? 0. K starts at 0. Okay? Now, for the n plus 2. When n is 1, this will be 3. Well, if k is 0, and I add 3 to it, then it'll be 3. Okay? Now the subscript of c. When n is 1, that subscript will be 1. Well, when k is 0, that's 0. Plus 1 will give me my 1. So there it is. Now, what you need to do is look at what k starts with in each of these. In the first one, k is starting with 4. And in the second one, k is starting with 0. So between 0 and 4, the largest number is 4. So we want to write both of these summation signs starting at 4. That one isn't starting at 4. But nonetheless, we're going to write it starting at 4. So that means that we're going to be leaving off some terms. Like when k is 0 and 1 and 2 and 3. When k is 0, you're going to have 0 plus 3, which is 3. C, 0 plus 1 is 1. And then you're going to have times x to the 0. But remember, x to the 0 is 1. And multiplying by 1 doesn't do anything. That's what this is when k is 0. Now we're going to add, let me move this more to the left. And then we'll add on when k is 1. This was where k is 0. Now k is 1. So 1 plus 3 is 4. And 1 plus 1 is 2. And x to the 1, which is just x. And now k is 2. I did 0 and 1. 2 plus 3 is 5. C. 2 plus 1 is 3. X squared. And now k is equal to 3. 3 plus 3 is 6. C. 3 plus 1 is 4. And x to the k, and k is 3. Okay. So I did that hopefully nicely. I'm going to write it down a little bit closer together so I'll have more space. And then we'll add up the rest of the pieces. And all of this, and we didn't even talk about how to solve these differential equations. Okay, plus this piece, the summation as k goes from 4 to infinity of k minus 2 times k minus 3 times c sub k minus 1 x to the k, plus the next summation. But I wrote down the first few terms. I wrote down from k equals 0 to k equals 3. So now I have to pick up where k equals 4 all the way to infinity. And the rest of this doesn't change. It's k plus 3, c sub k plus 1, x to the k equals. I write down the first few terms that I have in front. I suspect this was supposed to be x squared. Now, plus this mess. But the summation starts at the same place. The summation as k goes from 4 and it ends in the same place. So it's basically that summation that I just written down of this plus that. But the this and the that have an x to the k factor in common. So I'm going to factor out the x to the k. And what survives is everything but what's in red, namely the k minus 2 times the k minus 3 times c sub k minus 1. Need some more space. Plus this stuff without the x to the k because I factored it out. K plus 3 times c sub k plus 1. And that is what you get when you add this to that. Now, for the record, this answer on the very bottom is not unique. Okay, it's not unique. I could have rigged it where I started at 5, or 3, or 29. But we're going to leave it starting at 4. Of course, if I messed with where it started, well then that power would change. Like remember, that power must start at 4. I mean, after all, when k is 4, that power would be 4. So if I wanted to start at 29, if I wanted for some strange reason to start at 29, k goes from 29 to infinity. What's in that big red box, red brackets if you prefer, what's in here, lots of things will change. But what will change over here is it would be k minus 25. Why? Because if I plug in 29 and I take away 25, I get 4. And for example, when I plug in 4, I get 2. So this would have to be k minus 27. That would become k minus 27, only because 29 minus 27 is 2. But two different students can do everything correctly and get different answers. So, to be honest, I did say at the beginning we wanted to end up with the summations both having x to the k. So now we're in a position where we could start doing differential equations. Doing means solving. And it's a mess, but it's doable. Suppose you have y double prime plus x squared y is equal to 0. Now, we are going to assume that the solution is a power series. That is, it's a summation of c sub n times x to the n, where n goes from 0 to infinity. Now, when you have a sum and you take the derivative, you can take the derivative one by one. That is, still going to, the first derivative, is still going to be the summation as n goes from 0 to infinity. And just take the derivative of this. If you have a number times x to the n, you want the derivative, you multiply those two, and then you make the new power 1 less. Just like if you had 7x cubed. The c sub n is like the 7, and the n is like the 3. You end up with 7 times 3 x squared. Fair enough, you would never say 7 times 3, you would say 21x squared. So we're going to get n c sub n x to the n. Now, we wanted the second derivative, n minus 1 of course, just like I wrote here. You bring down the power, so it's going to be n times n minus 1 times c sub n, and the new power becomes 1 less. Now, for whatever it's worth, when it comes to, say, the derivative, I don't have to start at 1. Sorry, I don't have to start at 0. I can start at 1, and I'll explain why in a moment. Because when n is 0, that's going to be 0. Because 0 times some number is 0. Times x to the negative 1 is still 0. So this is really 0. That's the first term, plus the summation as n goes from 1 to infinity of n c sub n x to the n minus 1. All I did was break off the first term. But it turns out that when you add them, you get this. Same thing with the second derivative. Let's actually label it. The same thing with the second derivative. n minus 1 c sub n x to the n minus 2. when you plug in 0, this times this times this times that will be 0. Why? Because that's 0. That's when n is 0. Plus, now when n is 1, it'll be this times this times this times that. But that will be 0. After all, 1 minus 1 is 0. So when you multiply these, you're still going to get 0. Plus the summation when n goes from 2 to infinity. I just broke off the first two terms. And they actually equal 0, so you don't need to add them on. This mess is equal to this mess. Don't ask me why I didn't write down the initial factors. It's going to be n times n minus 1 cn x to the n minus 2. The only difference between this and that is this one starts at 0 and this one starts at 2. The reason they're still equal is only one reason. Because when n is 0, this mess is 0, and when n is 1, it's 0. Okay. So what we want to do is write down this equation at the very top using sigma notation. It is y double prime n goes from 0 to infinity plus x squared times y. Well, this is y. This is y. And when I multiply it by x, I get one more. Just remember, if you have x times this summation, it's x times the summation. It's c0 x to the 0 plus c1 x to the 1 plus c2 x squared, c3 x cubed, etc. But you could distribute the x, and you get c0x1 plus c1x2, excuse me. When you do x times c1x, get c1x squared plus c2x cubed plus c3x to the 4th, etc. And in terms of sigma notation, I notice that every single term has a c and an x. So it's going to be the summation of cx. And then I notice that this is 0, and then 1, and then 2, and then 3. So if I call this n, this has to start at 0. And it goes all the way up to infinity. And I notice that whatever I have there is one more on top. Whatever I have for the subscript to c, the power of x is one more. So if that's the subscript to c, then the power of x is one more. And this here is exactly what I wrote. So this is correct. And this last line that remains, since it's y prime, y double prime, plus xy prime, plus x squared y. This is y double prime plus x squared. Lovely, so this should be x plus 2 because if you have x squared, I said x. You have x squared and you multiply it by this. This can come inside the summation sign. Cleaning this up, we have cn times this times that. So this times that is that. And this equals 0 because x y double prime plus x squared y is identically 0. Now, what I want to do is add those two summations, just like we practiced at the beginning. So what I want to do is I'm going to have the summation as k starting at some number and going to infinity, and I'm going to have x to the k. Now, as I mentioned before, and here's the time where we want to invoke it, I said that n could have started at 2 because the first two terms would have been 0 anyway. Okay, so now when n is 2, that power will be 0. It's 2 minus 2 is 0. So if this power is k and I want it to start at 0, I should let k start at 0. Okay, so we're now starting at 0. Fine. Well, when n is 2, that term should be 2. That factor should be 2. Well, since k is 0, I'll do k plus 2. Now you can say that's 1 less. Well, if you have k and then somebody gives you 2 more, and then they take away 1, you're going to have k plus 1. You're going to have k plus 1. Now, if n starts at 2, I mean, you can argue, and you really should, that those two are the same. You have k plus 2, you're going to have k plus 2 again. And we already dealt with the x to the power. Plus another summation. Now, when n is 0, that power is going to be 2. And since I want x to the k, I should let k start at 2. If the k starts at 2, well then of course that will be 2. Now, n should start at 0. The subscript should start at 0. Since k starts at 2, I should have 2 minus 2. And there it is. Now, between these two numbers, 0 and 2, 2 is the winner. That is, what I'm going to do is break off the first two terms from here. When k is 1, you have 0 plus 2 times 0 plus 1. 2 times 1 is 2 times c sub 2, because 0 plus 2 is 2 times x to the k. That's when k is 0. Now when k is 1, you have 1 plus 2, which is 3, times 0 plus 1 is 1, and 1 plus 1 is 2, 3 times 2 is 6, c sub 3. So if k is 1, 1 plus 2 is 3. And that's when k is 2. And over here, k was 0. So we don't even need that term. Okay. Plus, now, so that was when k is 0, plus k equals 1. And now we're going to do from k equals 2 to infinity, all in one shot. That is using sigma notation. Well, what we're adding up doesn't change. It's still k plus 2, k plus 1 times c sub k plus 2 times x to the k, plus this. Summation k goes from 2 to infinity, c sub k minus 2 x to the k. So I write down the first few terms, and I get tired because here k was 1. Now I add on this, but they both have the same exact sigma. Sigma goes from, k goes from 2 to infinity. We're summing from 2 to infinity. So I have this plus that, the summation of this plus that. But this plus that happens to have x to the k in common. So I'm going to factor it out. I'm going to factor out the x to the k. Now remember, all of this stuff equals 0. Okay. So we need to get rid of an awful lot of stuff. We want this to equal 0. Now, one way it can equal 0 is if this is 0 plus 0 times x plus if that's 0. Because if you have the summation as k goes from 0 to infinity of 0 times x to the k, well, summation 0 to infinity, 0 times x to the k is 0. So when k is 0, that equals 0. Plus, when k equals 1, that equals 0. Plus, when k equals 2, that equals 0. You keep adding up zeros, well, it shouldn't actually end. If you keep adding up zeros, it's going to add up to 0. So let's write this down. We want 2 sub c2 to equal 0. Well, that implies c sub 2 is 0. And if you want 6 c3 to equal 0, that implies c3 is 0. There's only one number you can multiply 6 by to get 0. And we also want k plus 2 times k plus 1 times c sub k plus 2 plus c times k minus 2. We want this to equal 0. Now, you want to solve that last equation that we have on the top, the second one. We want to solve it for the subscript of c that's the larger one. In other words, I want to know something like c sub 7 is 3 times an earlier term. I don't want to know that c sub 2 is 1/3 of a later term. I want to get a later term in terms of the earlier one. This term depends upon, the value of this term depends upon an earlier term. For example, if c sub 2 is 4, then I know c sub 7 is 12. 3 times 4 is 12. So you want to solve for the subscript that's larger. Now I admit we don't know what k is. Here's some number k in a number line. K plus 2 will be there. And k minus 2 will be here. And regardless of where you are in a number line, whether you're looking at 2 positive numbers or 2 negative numbers, or 1 positive or 1 negative, 1 0, the other positive or negative, it's always true that the number to the left is less than the number to the right. The number to the right is always larger. So I want to solve for this. That is, first, I want to solve for that term. That means I bring that over to the other side. That's just what it means. K plus 2 times k plus 1 times c sub k plus 2 is equal to negative c sub k minus 2. Then I divide by what I don't want. And there it is. That's called a recursion formula. C sub k plus 2 is equal to negative c sub k minus 2 over k plus 2 times k plus 1. Okay, did a lot of work to get that formula. And now we go at this. We're going to use this information almost exclusively, except we're also going to use that information. If k is equal to 0, well then 0 plus 2 is 2. So c sub 2 is equal to negative c sub k minus 2. So so we need to decide where we start from. And what you want this to be is 0. You want that to be no smaller than 0. You want k minus 2 to be bigger than 0 or equal to 0. That means k must be at least 2. So we start at 2. 2 plus 2 is 4. And then 2 minus 2 for the subscript is 0. And k is 2. 2 plus 2 is 4 times 2 plus 1 is 3. So that is C4. It's in terms of C0. Now, when k is equal to 3, 3 plus 2 is 5, minus, it says minus, c sub k is 3, 3 minus 2 is 1, over 3 plus 2 times 3 plus 1. That is c sub 5. Now, when k equals 4, let's see what we get there. And we keep doing this until we see a pattern. When k is 4, well then 4 plus 2 is 6. C sub 6 is negative. C sub k is 4. So 4 minus 2 is 2 over 4 plus 2 times 4 plus 1. But now this is equal to 0 because c sub 2 is 0. Negative 0 is 0 over 30. That's 0. So c sub 6 is 0. And for the record, so we have c sub 2, we have c sub 3, we now know c sub 4, 5, and 6. But those are in terms of c sub 0 and c sub 1. And they're all going to be in terms of that. The ones that at least are in 0. If k is 5, 5 plus 2 is 7. It's negative c sub 5 minus 2 is 3 over 5 plus 2 times 5 plus 1. But c sub 3 is 0. So that's 0. And what's going to happen is this is going to kind of repeat. We're going to start seeing a pattern. Or at least you have to start seeing a pattern. If you don't see the pattern, you're stuck. You're dead. You can't do these. You're going to have to start practicing to recognize patterns. It's fun. Pattern recognition is fun. K equals 6. So this subscript will be 8. So C sub 8 is equal to negative C sub 6 minus 2 is 4 over 6 plus 2 times 6 plus 1. But here's where it gets a little bit tricky. This is negative 1 over 8 times 7 times C sub 4. But I know what C sub 4 is. It's this. It's negative C sub 0 over 4 times 3, which becomes positive 1 over 8 times 7 times 4 times 3, C0. That's what C8 is. Now, when K is equal to 7, well then 7 plus 2 is 9. We have C sub 9 equals negative C sub K minus 2. 7 minus 2 is 5, divided by K plus 2, that is 7 plus 2, times 7 plus 1. Okay, so this is really negative 1 over 9 times 8 times that, C sub 5. But that's C sub 5. It's negative C1 over 5 times 4, which is 1 over 9 times 8 times 5 times 4, C1. That's how many C1s we have. That's K equals 7. And to save a little space, let me write it up here. We have C1 over 9 times 8 times 5 times 4. Okay, let us find out what happens when K is equal to 8. When K is equal to 8, 8 plus 2 is 10, minus C sub 8 minus 2 is 6, over 8 plus 2 times 8 plus 1. Again, we get negative 1 over 10 times 9 times C6. But C6 is 0. C6 is 0. And when you multiply that number by 0, you get 0. So C sub 10 is going to be 0. And when K is 9, you get C sub 9 plus 2 is negative C sub 9 minus 2 over 9 plus 2 times 9 plus 1. So you get negative. Now C sub 7 is 0. It's negative 0 over whatever, 110 or 11 times 10. But the bottom line is it's not 0. And 0, that's 0. And you're dividing it by a non-zero number, you get 0. C sub 11 is 0. C sub 11 is 0. Now, I want to move over C sub 8. This is equal to C sub 0 over 8 times 7 times 4 times 3. And that's another group of 4. And I do see some pattern The last ones are 0. The ones before last are 0. And the next one up, they're all multiples of C1. And then the one above that are multiples of C0. Now, let us see what happens when k is 7. I'll do that on the bottom, and then I'll transpose it higher up. When k is 7, you get, I'm always reading this one here. C sub 7 plus 2 is negative C sub 7 minus 2 over 7 plus 2 times 7 plus 1. And I don't know why I did that, because we did k equals 6, 7, or you did 7, 8, 9, and here I should be doing k equals 10. So if k is 10, I have c sub 10 plus 2 is negative c sub 10 minus 2 divided by 10 plus 2 times 10 plus 1. So it's negative 1 over 12 times 11 times c sub 8. The c sub 8 is right there. It's c0 over 8 times 7 times 4 times 3. We have that c sub 12 is negative 1 times c0 is that over 12 times 11 times 8 times 7 times 4 times 3. That is c sub 12. And that occurred when k was 10. Now, when k is 11, it's going to be c sub 11 plus 2, 13. It's going to be c sub 13. And it equals to negative c sub 11 minus 2 over 11 plus 2 times 11 plus 1, which is negative 1 over 13 times 12 times c sub 9. But this here is c sub 9. Got it right from here, folks. So c sub 13 is equal to negative 1 times c1, negative c1, all over 13 times 12 times 9 times 8 times 5 times 4. That number right here was a 4. So it should be a 4 there. That's c sub 13. Now, c sub 14 is going to be 0, because this happens when k is equal to 12. 12 plus 2 is 14. And we get negative c sub 12 minus 2 is 10 over k is 12, so it's 12 plus 2 times 12 plus 1. But c sub 10 is 0. It's going to be 0 divided by whatever that product is. That's 0. C sub 14 is 0. And when k is 13, c sub 13 plus 2 is going to be negative c sub 11 over 15 times 14. But c11 is 0. So c sub 15 is going to be 0. Now is where you have to start being clever. I keep having patterns of 4. I keep having patterns of 4. I think the 4 times table. You're going to have c sub 4n, that is the remainders when you divide by 4 or 0, or the 4 table, which of course is 0, 4, 8, 12, 16, and then you're going to have multiples of 4 plus 1, which would be 1 and 5 and 9 and 13 and 17. 4 times 0. So it's 1 more than the 4 table. The 4 tables on top and the numbers right below are 1 more. And then you have 2 more than the 4 table. 2, 6, 10, 14, and then 18. And then lastly, you're going to have 3 more than the 4 table. And this is going to be 3 and 7 and 11 and 15 and 19. And of course, each of these lists goes on and on and on. Well, if you notice something, I have every number. I have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, etc. I have all the numbers of all of them. Now, if you look at this number, it's 2 more than a number on the 4 table. It's 4 times 1 plus 2. And this number here is 4 times 2, 8 plus 2. And this 14 here is equal to 4 times 3 plus 2. The 4 times 1 is on the 4 table, 4 times 2 is on the 4 table, 4 times 3 is on the 4 table. So those numbers are 2 more than numbers on the 4 table. And they all equal 0. That is, that's always 0. And you know what? This number and this number and that number are 3 more than numbers on the 4 table. 4 times 1 and then 3. 4 times 2 is 8 plus 3 more. 15 is 4 times 3 is 12 plus 3 more. If you're 3 more than a number on a 4 table, you're 0. Okay, these two terms are always going to be 0, no matter what n is. Okay, if n is 10, 40 plus 2, 42, c sub 42 will be 0. If n is 11, 4 times 11 is 44, plus 3 more is 47. C sub 47 will be 0. Okay, so that's good. Let me somehow sneak that in on top. C sub 4n plus 2's is equal to C sub 4n plus 3's, which are always 0. Okay, so what about 4n and 4n plus 1? Let's look at the 4n's. Let's look at the 4n's. Now, the last 2 rows I could erase because they were all zeros. So that was very helpful to be able to get rid of them. Okay. This is 13 times 12 times 9 times 8 times 5 times 4. Somehow it got erased. Now, let's look. So there's a brick, there's a division line here. Now like 4 divided by 2. The numbers above this, now red line, Those are pure multiples of 4. The subscripts are all multiples of 4. And the ones below are one more than multiples of 4. And the ones that are multiples of 4 all have C sub 0. I see that. And the signs alternate. First it's negative, then it's understood to be positive, and then it's negative. Okay, we'll worry about the alternating signs. But what I want to see is what's going on with the denominators. We have 4 times 3, 8 times 7 times 4 times 3, 12 times 11 times 8 times 7. Maybe we'll look at that one. What I noticed is they have the multiples of 4. 4, 8, and 12. 4, 8, and 12. Oh, look, look, look. The 12 is being multiplied by 1 less. The 8 is being multiplied by 1 less. And the 4 is being multiplied by 1 less. In other words, if you had 16, you'll have 4 times 8 times 12 times 16. But you also will have 1 less than the 4, 8, 12, and 16. If it went up to 24, 24, 20, 16, 12, 8, and 4. Those are the multiples of 4, up to 24. And then you also multiply by 1 less, which of course should be 19. You multiply by 1 less. Now, we really should verify that that happened with the other ones. Okay, when it was C sub 8, you have 4, 8, and 1 less. 1 less than 8, 7, 1 less than 4 is 3. Oh, look, that's exactly what the bottom was. And when you have C sub 4, that's the only number on the 4 table we're going to have, times 1 less. That's exactly what's on the bottom. Okay, so now how do we write this up? So these subscripts 4, 8, and 12, they are multiples of 4. They are multiples of 4. We'll talk about the plus minus in one moment. We're going to have 0 on top, and then you're going to have 4 times 1 less, dot, dot, dot. Eventually you'll have 4n times 1 less. Now, how do we handle their minus sign? Well, if the signs are going to alternate, it's going to be -1 to a power. Well, remember, 4, the first subscript, is 4 times 1. 4 is 4, and n is 1. And then you're going to have 8, C sub 8, which is 4 times 2. So you have 4 times n, that is, n is 2. And you'll have 12, C sub 12, which is 4 times 3, and eventually 16, which is 4 times 4. These 1, 2, 3, 4, etc., those are the n's. For the record, I don't want you to think you can't go above 4. 20 is 4 times 5. The n is 1 and 2 and 3. Well, if you do -1 to integers, consecutive integers, the sign oscillates. If I put 1 here, well then when n is 1, negative 1 to the 1 is going to be negative 1. And then when n is 2, you're going to have plus 1. And when n is 3, you're going to have negative 1. Just like we want. We want the sign to start off negative and then become positive and then become negative. That is the formula for the C sub n's where n is a multiple of 4. Now what happens when n is a multiple of the subscript is one more than a multiple of 4? So what we want to look at are these terms, C5, C9, C sub 13. Now, ignoring the fact that the C1 on top is oscillating, we always have C1 on top. And for the bottoms, for C sub 5, the bottom is 5 times 4. For C sub 9, the bottom is 9 times 8 times 5 times 4. And for C sub 13, it's 13 times 12 times 9 times 8 times 5 times 4. Well, having just done the last one, the C sub 4n's, you should say, wait a minute. This has 4. This one has 4 times 8. This has 4 times 8 times 12. But there's other numbers. Oh, look. There's always one more than what's in red. 4 plus 1 is 5. 8 plus 1 is 9. 4 plus 1 is 5. 12 plus 1 is 13. 8 plus 1 is 9. 4 times 5. 4 plus 1 is 5. So we're multiplying multiples of 4 and also multiplying one more than the multiple of 4. So in the bottom, you're going to have 4 times 5, and then 8 times 9, and then 12 times 13. Okay, and eventually you'll have 4n, and then you multiply it by one more. You keep multiplying multiples of 4, and also one more than multiples of 4. But you stop at 4n. The last multiple of 4 is 4n. And the one above, the last multiple of 4 is 4n. Okay, so now, if I don't erase anything I shouldn't, but now we're ready to write down the solution. We said from the very get-go that we're going to say that y is the summation of c sub n times x to the n, and then goes from 0 to infinity. We did say that. Okay. We also said that c sub 4n plus 3 was 0, and c sub, well, that is true, but let's go in order. 4n plus 2, and c sub 4n plus 3 is 0. So half of these terms, we have the c sub n equals 0, and when you multiply it by x to the n, it's still going to be 0. Just remember that this one has 4 and 8 and 12 and 16, and this one has 9, 9, 13, and 17. Okay. And we did forget one thing. The sign oscillated here, and it's also negative 1 to the n. It's also negative 1 to the n. Okay. So we get C sub 0. Now notice C sub 0 and C sub 1, they can be anything we want. They can be anything we want. And whatever we get in the end, whatever we plug in for C0 and C1, it's going to work. Okay, so we have C0 plus C1x plus C1x plus C2x squared. But remember, C2 is 0 plus C3 x cubed, but C sub 3 is 0. And now we start using what I have boxed down here. We start using this and that as well. We're going to talk about C sub 4. C sub 4, that's when n is 1, and that's an odd number. Negative 1 to an odd number is negative. So it's going to be negative C sub 0 over, let me just write x to the 4. So it's going to be 4 times 3. And now x to the 5th is going to be negative, because we're down here for 5, and negative, that means n is 1, because 4 times 1 is 4, plus 1 more, n is 1, and negative 1 to the n, negative 1 to the 1 is negative 1, times C1 over 4 times 5. That's going to be x to the 5. And let's write down some more. Now, x to the 6, well, that's that type of number. And x to the 7 is that type of number. This is going to be 6 and 10 and 14. This is going to be 7 and 11 and 15 and 18 and 19. So 6 and 7 are 0. Now we have 8. 8 is 4 times 2. So n will be 2, which is even, so it's plus. Plus C0 x to the 8 over, since that's 8, we do 8 times 4, but for the C0, we go 1 less. 8 times 7 times 4 times 3. And now we did C8. Let us do C sub 9. C sub 9, that's 4 times 2. 8 plus 1. Well, 2 is even. Negative 1 squared is going to be plus C sub 1 over 4 times 8. But for the C1s, we bump up the 4 and the 8 by 1. 4 times 5 times 8 times 9. That's 9. And then 10 and 11, those are 0. Now we come to 12, which is 4 times 3. 12 is 4 times 3. The n is 3. Negative 1 to the 3 is negative 1 times C0. And we're doing 12. So it's 4 times 8 times 12. For the C0s, we always go down 1. 4 times 3, 8 times 7, 12 times 11. That was 12. Now we do 13. Well, 13 is 4 times 3, 12 plus 1. The n is 3. Negative 1 to the 3 is negative. Negative C sub 1 over 13. Well, that's 4, 8, 12. And for C1s, we always go up 1. 8 plus 1, 12 plus 1. And we continue like this forever. Now, the one last thing I want to do is split this up into two sums. Part that has C1 terms and not C0 terms. For C0, I can factor it out. It's C0 times 1 minus x to the 4 over 4 times 3 plus x to the 8 over 8 times 7 times 4 times 3, etc. minus x to the 12 over 4, 3, 8, 7 times 12 times 11, etc. plus the C sub 1. C sub 1 times x minus C1 x to the 5th over 4 times 5 plus, now this should be x to the 9 this should be x to the 12 and this should be x to the 13. So plus, I factored out the C1, there's the x to the 9th over 4 times 5 times 8 times 9 minus this term. I factored out the C1, x to the 13, 4 times 5, 8 times 9, 12 times 13, etc. Now so this is one solution. In fact, we can even write it down as two solutions. Y equals that, y sub 1 equals, what it says. This is one solution, and y sub 2 equaling that is another solution. The linear combinations of c sub 0 and c sub 1. And there's the solution. You need to practice these to see their patterns. And unfortunately, you can't study to see patterns. I guess the best way of learning patterns is to look at a lot of workout examples and starting to get better at seeing patterns. Okay, so let's consider this problem. Y double prime plus 2xy prime plus 2y equals 0. And we're going to say, now this has x and y primes. So we can't use the technique of our last section. So we try this new technique. Y is equal to the summation as n goes from 0 to infinity of c sub n x to the n. And y prime is the summation as n goes from 0 to infinity of nc sub n x to the n minus 1. Now, there's no point in starting with 0 because when you multiply those three factors, and one of them is 0, and n is 0, the factor n, that factor is 0, the whole thing will be 0. So we can get away with starting at 1. And if we were to take the next derivative, we would get the summation as n goes from 1 to infinity of n, bring down the n minus 1, c sub n, x to the n minus 2. Well, there's no point in starting at 1 because when you multiply 1, 2, 3, 4 factors, and one of them is 0, the whole thing is 0. And of course, the second factor, n minus 1, will most definitely be 0 when n is 1. After all, 1 minus 1 is 0. So we can start off with 2. So I'm going to rewrite this using sigma notation. Y double prime is the summation as n goes from 2 to infinity of n times n minus 1 times c sub n times x to the n minus 2. Now 2x times y prime, where this is y prime. Remember, this here is the summation. Is 2x times one thing plus another thing plus another thing all the way down forever. Well, the 2x gets to be multiplied by each of those things. That is, I can just add up and then goes from 1 to infinity of 2x times n cn x to the n minus 1. And remember, when you're multiplying things, the order doesn't matter. You can multiply the 2, the n, and the cn first. There it is. And then multiply the x by the x to the n minus 1, which is x to the n. So this here is 2xy. It's 2x times y. So let me write it down. The summation, and then goes from 1 to infinity of 2 sub n, c sub n, x to the n. And now I add on 2 times y. Well, here is y, and same argument. This 2 that's in front, I can put after the summation sign. Okay. Now I want, one last thing. This goes from 0 to infinity, because that's what y started with, 0. And multiplying it by the 2 won't affect that. So now I want each of those power series, each of these infinite series, to have x to the n. I meant to say x to the k. But since these two have x to the n, it's easy to get x to the k. Just replace every n with k. And unfortunately, they were all just n. They could have been n plus 3, and then I would write k plus 3. So for right now, that's how I write k. The summation as k, n goes from 1 to infinity of 2 times n times 3 sub n times x to the n, plus, same game over here. The summation as n goes from 0 to infinity of 2 c sub k x to the k. I mean, if you wanted to do it the way that I was doing it earlier, to verify everything, you can do that. Maybe I don't know where k starts with, but I want x to the k. Well, if n starts with 1, then that power will be 1. That is, okay, so if I want this power to be 1, I should let k be 1. The 2 won't change. When n is 1, that's 1. So I want to put 1 here. K starts at 1. And I'm supposed to start at c sub 1. Well, if k starts at 1, I'll just put c sub k. If you notice, all that happened was n became k. N became k. But unfortunately, that's not true in the first summation because it's not x to the n. But nonetheless, I want to get x to the k. Now, if n starts with 2, that means the power starts at 0. Well, if I'm calling the power k, I better have k starting at 0 and absolutely going all the way to infinity. So k starts with the value 0. Well, n is going to start with 2. I want this to start with 2. So instead of k, which starts at 0, I'll add 2 to it. Now, that's 1 less. So 1 less than k plus 2, k plus 1. c sub n. Well, we just did n. There was n. That is, these two are supposed to be the same. Oops. Those two are supposed to be the same. And since I learned that n becomes k plus 2, well then n becomes k plus 2. So now every one of my summations is being multiplied by x to the k, which is good. Now I need to get the subscripts to be all the same. I need to get them to be all the same. Well, what I meant was what k starts with. Here k starts with 0, and then 1, and then 0. The largest number is 1. So this one's wonderful. I don't have to do anything with that term. I don't have to do anything with it. Now, we can be a little bit slick here and know that we can always add 0. See, we have the summation as k goes from 1 to infinity of 2k c sub k x to the k. But you know what? This is equal to, well, let's not say that. Let's say it. This is 0 plus the summation of 2k c sub k x to the k, where k starts at 1 to infinity. But this 0, I can think of it as 2 times 0 times c sub 0 times x to the 0. That is, I wrote this where k was 0. And this is 0. That is, this whole sum, that sum right there, is the summation as k goes from 0 to infinity of 2k ck x to the k. And again, the reason is that when I plug in 0, when I plug in 0, that's 0 anyways. That is, instead of starting at 1, I can start at 0. The nice thing now is all my summations are starting with 0. Now remember, this was y prime, that was y double prime, plus 2x y prime, plus 2y. It was this. And it does say it equals 0. Now that all my summations are starting at the same value, I can write it as one summation. Summation as k goes from 0 to infinity. And in addition, they all have one factor in common. They might have others, but I'm only concerned about that factor. Okay, so I can factor that out. So I'm going to have this number of x sub k's plus that number of x raised to the k, x raised to the k's, plus that number, x to the k's, and that equals 0. So basically, I want this to be 0. Now, when it comes to 2k c sub k, this term plus that term, I'm really adding c sub k's. I can factor out a 2. And then inside that bracket, I can say that I have k plus 2 c sub k's. 2 times k plus 2 c sub k. Now what's inside those big brackets, I want it to be 0. K plus 2 times k plus 1 times c sub k plus 2 plus 2 times k plus 2 times c sub k. I want that to be 0. And now the second phase of the problem starts. Finding the c sub k's, or the c sub n's. Remember, our solution is the summation of c sub n x to the n. I need to find the c sub n's. So it's this term plus this term is equal to 0. So I want to solve for the factor that has the largest power of k. This is just k, but that's 2 more. So I want to solve for c sub k plus 2. So first I'll solve for this term. K plus 2 times k plus 1 times c sub k plus 2, bringing that to the other side, is negative 2 times k plus 2 c sub k. I'm going to divide by the factors I don't want. K plus 2 times k plus 1. And coincidentally, this cancels out. So again, negative 2 c sub k over k plus 1. So let me write that down here. This is equal to that. Negative 2 c sub k over k plus 1. That's utmost important. Gotta be able to get there. Okay, we have this. Now, what's the least value that k can be? Well, you can only have C0s and C1s and C2s, etc. Why can't you have C sub negative 5? The answer is, y is the summation is n starts at 0 to infinity of C sub n, x to the n. This can only be 0 or 1 or 2 or 3. So the k plus 2 has to be, or when is it? 0. It has to be bigger than or equal to 0. The k there has to be bigger than or equal to 0. And we know one thing, the bottom can't be 0. You can't divide by 0. Now, let's just say for the moment we had k plus 4. Well, that means k equals negative 4. Well, you can't start at negative 6, or let's even say k minus 4, okay? So k equals 4. You have to start at more than 4, because if you started at 3, I mean, after all, if k can't be 4, it can be 3. So this will be negative 1. You can divide by negative 1. We're making believe that bottom is k minus 4. But the problem is then, after k equals 3, k is going to be 4. We want that to be bigger than 0. We want the bottom to be bigger than 0. So k has to be bigger than negative 2. K has to be bigger than 0. And bringing the 1 over, k has to be bigger than negative 1. Now, if I'm thinking of and these all have to be true at the same time. If I tell you, if you guess the value for k, you get an A in your differential equation class. And you come and I tell you three pieces of information. I tell you K is bigger than -1, K is 0 or bigger, or K is -2 or bigger. All three have to be true. K has to be -2 or bigger, and K has to be 0 and bigger, and K has to be bigger than 1. Well, where are they all true? They're all true from 0 on. K has to be at least 0. Okay. You need to be able to do that because you have to know where to start. So if K is 0, 0 plus 2 is 2. And it equals to -2 C0 over 0 plus 1 or 1. The rule for dividing by 1 is don't bother. So that is what C2 equals. Now when K is 1, 1 plus 2 is 3. C3 is -2 C1 over 2. C sub 3 is -C1. C sub 3 is -C1. Now, when K is equal to 2, 2 plus 2 is 4. It equals to -2 C sub K over 2 plus 1, which is 3. And the only thing is we know K is 2. So that's what C sub 4 equals. Now, when K is equal to 3, we're going to have 3 plus 2 is 5. Now, you can be clever. You can say, you know what? First the subscript was 2, and then 3, and then 4. So here it's going to be 5. They all have a -2. They all have an equal sign. They all have an equal sign. They all have a -2. They all have a division line. So that's over 1. They all have a division line. And then they all have a C. They all have a C. C0, C1, C2. Oh, that must be C3. The dividing by 1, 2, 3. But here we can say something a little bit more. We know what C3 is. It's -C1. So this will become 2C1 over 3. Now, when K is 4, you're going to have C6 equals to -2 C4. Now, of course, we have a little typo here. Try to be slick. We're dividing by 1, and then 2, and then 3. I don't see why here we shouldn't divide by 4. Now, since we always have a -2 in the top, or a +2 in the top, I'm not going to really do the division there. Okay, so this is going to be over 5. But C sub 4, we know what C sub 4 is. It's that. It's -2 C2 over 3. So we get 4 C2 over 3 times 5. And I'm going to write that a little bit closer for obvious reasons. I get 4C2 over 3 times 5. And I want to check the last one. I have -2/4 times C sub 3, which is -C1. So this should be over 4. Now, when it comes to C sub 4, it equals to negative 2/3 times C2. But I didn't realize we have C2. It's negative 2C0. So we get 4/3 C0. So C sub 4 is equal to 4/3 C sub 0. That's C sub 4. Actually, I want to do the division here. I get 1 over 2. Okay, now C sub 6 is what I have, I suspect. Well, let's do C sub 6 again. C sub 6, using the rule, so K is 4. 4 plus 2 is 6. I get negative 2C4 over 5, which is negative 2/5 times C4. And C4 is 4/3 C0. So I get 8 over 3 times 5. I get 8 over 3 times 5 C0. Okay, let's do some more. When K is equal to 5, see the side work here. I get C sub 7 is negative 2 C sub 5 over 1 more. So it's negative 1/3, that's negative 1/3, times C sub 5, which is this. It's C1 over 2. So I get negative 1 over negative C1 over 3 times 2. C sub 7 is negative C1 over 3 times 2. Now, let's see if we have a pattern. What I notice is that every other term either has C1 and the other term has C0. For example, take C2, C4, C6, they all have C sub 0. You have negative 2, it's right here, negative 2C0 over 1. You have negative, you have 4 and then 8. So you have 4 is 2 squared over 3C0. And then here you have 2 cubed over 3 times 5 C0. Now, of course, I can always say 1 in front. I'm seeing a pattern for the numerator. And I'm wondering why C sub 6 is not negative. C sub 6 is, that means K is 4. So it's negative 2C4 over 5. So it's negative 2/5 times C4, which is 4/3 C0, which is clearly negative. Sorry, it's negative. Well, when I look at their numerators, ignoring the signs for a moment, I get 2 to the 1 C0, 2 squared C0, 2 cubed C0. When I look on the bottom, I see the product of the first few odd numbers. 1, then 1 times 3, and then 1 times 5. Now, where do I stop? Why don't I go 1 times 3 times 5 times 7 times 9? Well, when this was 6, I stopped at the first odd number before 6, which is 5. When this was 4, I stopped at the first odd number before 4, which is 3. And when the subscript was 2, I stopped 1 before. So it seems like C sub 2n, the evens. Well, we're going to have negative 1 to a power. That's going to oscillate. We'll talk about that one in a moment. O times C0. And in the bottom, that's the oscillating. Then we have 2 times C0. 2 to the n times C0. And in the bottom, I have the odd numbers up to 1 before the subscript. When the subscript was 4, I stopped 1 before. There's 1 times 3 all the way up to 2n minus 1. Now, let's make sure that this power right here is right. When it's 2 times 1, I want the power of 2 to be 1. Oh, it is. And when it's C sub 4, that is when n is 2 times 2. Four is 2 times n. N is 2. And I want 2 squared. And when it's C sub 6, which is C sub 2 times 3, I want the numerator to be 2 to the 3. It's working like a charm. It should always be 2 to the n. Now, when first n is 1, and then n is 2, and then n is 3, well, I want it to start off with a negative. So if I do negative 1 to the n, it'll be negative. And then when I do negative 1 squared, it'll be positive. And negative 1 cubed, it'll be negative. There it is. This is what happened with the even terms. Now remember, every odd number is an even number plus 1 more. 7 is 6 plus 1. 13 is 12 plus 1. You can think of every odd number as an even number plus 1 more. Now, what are the odd ones? We get negative C1, we get 1/2 C1, we get negative C1 over 3 times 2. Now you can do some more terms to believe what I'm saying. But there's a 1 here, and that equals 1 factorial. This denominator is a 2. That happens to equal 2 factorial. And 3 times 2 is 3 factorial. Now, if we let x equal 7, then we will have, using the rule up here, if we have k equals 7, then the rule up there will say c sub 7 plus 2 is equal to negative 2c sub 7 over 8. So c sub 9 is negative 2 over 8. Just write it as a quarter. It's negative 1/4 times c sub 7, which is negative C1 times 3 factorial. So you're going to get negative 1 times negative C1 is positive C1, and 4 times 3 factorial is 4 factorial. So it is correct when I say factorial, and you can do some more to verify it. So now, let's be careful now. C3, well, let's write down C1. C1 is negative C1 over 1 factorial. C3 is C1 sorry, that's C sub 3. C sub 5 is 1 over 2, C1 over 2 factorial. And C sub 7 is negative C1 over 3 factorial. So we're going to have to realize that when n is 1, that will give us 3. That's when n is 1. And when n is 2, 2 times 2 is 4, plus 1 more is 5. That's when n is 2. And if you work it out, this is where n is 3. After all, 2 times 3 is 6, plus 1 more gives you 7. Now, if you do negative 1 to the 1 to the n, where n is 1, you'll get a negative. And if you do negative 1 to the second, you'll get a positive. If you do negative 1 to the third, you'll get a negative times C1. Now, how do we go from the subscript 2n plus 1 to a factorial? How do you go from 3 to 1 factorial? How do you go from 5 to 2? How do you go from 7 to 3? Well, we've already broken down the subscript to 2n plus 1. We've already broken down the subscript to 2n plus 1. Well, when n is 1, when n is 1, we had 1 factorial. When n is 2, we had 2 factorial. When n is 3, we had 3 factorial. So, we have n factorial. That is how we write down C sub 2n plus 1. And that's it. These happen not in groups of 4 like the last time. It happen in groups of 2. So we have this, and I'm hoping I remembered. So this first one talks about C sub 2 and C sub 4 and C sub 6, etc. and etc. And the one below talks about C5, C3, C5, C sub 7, C sub 9, and so on. And the question is, did we have a leading term that was 0? In fact, no. Because when we had or solved for, let's see what that equation was. When we solved for y double prime plus 2xy prime plus 2y equals 0, what we had was the summation of some big mess times x to the k equaling 0. We didn't have something like 2c sub 2. Because if we did, then I would say c sub 2 is 0. So the free or open constants here are going to be c0 and c sub 1. And how about we break up? Remember we said y was equal to the summation of Cn times x sub n. How about we do the following? We break this up, and this was when n went from 0 to infinity. How about we do the evens? Remember, whatever the subscript is, the powers have to be, and n will go from 0 to infinity. So this mess takes care of C0 x to the 0 plus C2 x squared plus C4 x to the 4th, etc. And then we add on the odd terms, if I could call them the odd terms. The summation of C sub 2n plus 1 x to the 2n plus 1, where n again starts at 0. So that would give us 2 times 0 is 0 plus 1, give you C1x to the 1, and then n is 1. 2 times 1 is 2 plus 1 more is 3, and then it'll give you C5x to the 5, etc. And when you add them, when you add this to this, you actually get y. You actually get this. Okay, so that's just the logic behind it. Now, let's actually do this. So now remember, we get C0 plus C1x plus, now we deal with this up here. C sub 2, well that's when n is 1, you're going to get negative 1 to the 1, which is negative. Oh, actually, this one doesn't come up yet. We're just going to do these. So when n is 0, you get c to the 0 times x to the 0, which is just c0. And then when n is 1, we use this rule up here. You get negative 2 to the 1 c0 over 1 plus, now n is 2, so you get negative 1 squared, which is positive, and then you get 2 squared, c sub 0 over 1 times 3, and then you get minus 2 to the 4 c0 over 1 times 3 times 5, etc. Plus, now we do this term. So we have 1 is not part of this rule, but we're still going to have c1x to the 1 minus, now n is 1, that'll give us c sub 3 minus c1 over 1 factorial, which is just c1. c1 x sub 3 plus n is 1, this should be c sub 3, excuse me. And then now n is 2, so you get c1, no, actually this is c1, it's always c1. You get c1 x to the 5 over 2 factorial. This you can think of as over 1 factorial. This is over 0 factorial. We have minus c1 x to the 7 over 3 factorial plus c1 x to the 9th over 4 factorial, etc. And if you wanted two solutions, you can call this y1 and this is y2. Those are two solutions. And You can even from here factor out the c sub 0, and over here you can factor out the c sub 1. Lots and lots of silly arithmetic. Tons and tons of it. Subscripts, superscripts. You have to be able to do this. Just do a lot of these. Do 10 of these problems and you'll be okay. And fine, the first one's going to take you an hour. It certainly took me an hour to do my very first one. And then second one will be last, and then eventually you'll do them in 10 minutes. Okay, have fun. Good luck.